Welcome back to the Deep Dive. Today we are digging into a really fascinating contradiction at the heart of the race to AGI.
That's right. We're looking at the timelines.
Exactly. We've got a whole stack of sources here, articles, some expert analyses, even some internal lab notes, and we've put it all together for you, the learner, to really cut through the hype.
And our mission today is to analyze this huge gap, this dissonance between two things. First, you have the rhetoric, right? People talking about transformative, runaway AGI in, what, 5 years?
Yeah, these extreme short timeline predictions.
And then on the other hand, you have the actual methods, the clunky, incredibly expensive ways that the leading AI labs are currently building these models.
It's a massive contradiction. I mean, if a model was really, truly close to being a human-like learner, able to observe and reason and generalize from just a little bit of data.
Then this whole process would be pointless.
Right. The whole labor-intensive process of front-loading specific knowledge would be completely redundant. Why spend billions teaching it something it should just be able to figure out?
Exactly. And that's the key. The actions of these labs, well, they speak a lot louder than their public optimism. The methods they're using, they hint at an internal worldview where generalization is still profoundly difficult.
Which directly undermines the idea that a rapid, self-directed takeoff is just around the corner.
And we're going to focus specifically on this reliance on what's called reinforcement learning, or RL, from verifiable rewards.
Okay, so this cost of front-loading capabilities, that's the first thing that just jumps out from all the sources. And we're not just talking about the cost of the computers.
No, not at all. There's an entire supply chain and auxiliary industry that supports these highly manual mid-training environments.
What does that look like in practice?
Well, think of it like the labs are trying to hard code a massive curriculum. They're literally hiring specialized companies to build these bespoke virtual worlds just to teach the models very specific, very practical tasks.
Like what?
Things like how to navigate some opaque corporate terminal, or how to use Excel to build a really precise financial model from some obscure legacy data, or even just, perfectly crafting a client-ready PowerPoint.
That seems like an unbelievable expenditure of specialized human labor, if AGI were imminent.
It would be, right?
Yeah. Wouldn't you just expect the models to learn on the job, in a self-directed way? A 2-minute walkthrough video should be enough if it's that smart.
It absolutely should be, but that's the thing. That self-directed learning is still largely elusive. So the labs are forced to spend fortunes building these hyper-specific training pipelines.
So they're basically admitting that the model needs explicit instructions, not just raw data, to get skills that are actually useful in the economy.
Yes, before it's even deployed. It suggests a really, really labor-intensive path forward.
And Baron Milik's research on the financial cost here, it just hammers this point home. The sources suggest we really need to rethink what we mean by scaling.
We absolutely do. When you see a frontier model getting better at some benchmark, you can't just chalk it up to more computers or, clever research. The money being spent is staggering.
So what did Milik find?
He noted that we have to consider the billions of dollars that are paid to PhDs, MDs, and other experts to write questions and provide example answers and reasoning, all of it targeting these very precise, very complex capabilities.
Wow, so that sounds less like you're advancing a general learner and more like you're building the world's most expensive, specialized flashcard deck.
That's a great way to put it. It's a focused effort to just plug specific holes, not some foundational leap in learning efficiency.
And you can see this limitation so clearly in robotics.
Oh, absolutely. For years, we've been told that robotics is, a hardware problem? Or a data problem that's just a massive oversimplification.
I remember thinking that when the early models came out. I thought, okay, once we solve perception and language, robotics is basically solved. But that has not happened.
Because it's fundamentally an algorithms problem. It's
Yeah.
about efficient, generalized learning. I mean, a human can look at a new dishwasher and figure it out almost instantly. The fact that we still need robots to go out into 1,000 different homes and practice 1,000,000 times just to learn to fold laundry.
It proves we don't have a human-like general learner.
Exactly. If we had that, robotics would be largely solved. But these massive, bespoke training loops, they're still required.
So this huge investment in hard coding skills suggests we are nowhere near a rapid generalized takeoff. And that moves us from the cost of labor to the nature of the capability gap itself.
Right, the gap between having a general understanding versus possessing the specialized context and judgment you need for real-world work.
And that's a critical distinction. A model can ace the bar exam, but a real job, is all about this localized, specific judgment.
There's a great anecdote in the source material that illustrates this perfectly.
Hmm.
This dinner conversation between an AI researcher and a biologist.
Okay, set the scene for us. The AI researcher is a short timeline advocate, right?
Yeah.
Super confident, and the biologist is much more skeptical.
Exactly. So the biologist is asked why she has such long timelines, and she describes this common daily microtask in her lab. She's looking through a microscope, and she has to decide if this tiny little dot is actually a macrophage, a type of white blood cell, or if it's just some debris that looks like one.
Okay.
And here's the key.
Hmm.
It's all based on her lab's extremely specific, unique slide preparation method, their own chemical staining.
And what was the AI researcher's response to that?
He just immediately dismissed the complexity. He said, that's textbook image classification. That is dead center in the kind of thing that we could train these models to do. He totally missed the point.
Wow. And this is really where the disagreement crystallizes, isn't it? She's
Right.
not talking about general macrophage identification.
Not at all.
She needs contextual judgment
Mm.
based on the quirks of her single lab's protocol,
Mm.
which might change week to week based on, I don't know, the temperature in the room.
Exactly. Human value isn't just in raw classification, it's in that micro-contextual judgment.
Yeah.
And the trust you build around it. It is just not economically sensible to build a custom training pipeline for every single lab in the world just to identify one type of cell.
So to automate a job, you need that situational awareness, those skills you learn on the job that change every day. You can't just hard code every single decision tree.
Now, to be fair, there is a counter argument here. It does make sense to front load some general skills, right? Fluency with browsers, terminals, coding languages, that's efficient.
Sure, you don't want every company having to teach the model how to use Python from scratch.
Right. But people are, and this is a quote, underrating how much company and context-specific skills are required for most professional jobs. That layer of contextual knowledge, the politics of a client relationship, the weird quirks of a 20-year-old internal database, that is the huge unaddressed barrier.
And it's a barrier that the short timeline predictions just sort of gloss over.
They gloss over it completely.
And that contextual gap, that leads us right into the economic reality check. I mean, if these models were truly humans on a server, as some people say,
The diffusion rate would be insane, almost instantaneous.
far easier to onboard than a person. It could read your entire Slack and Drive in minutes and be ready to go.
And the economic implications, I mean, if the capabilities were really at AGI level, people would be spending trillions of dollars a year buying tokens. That is the metric to watch. Knowledge workers around the world make, what, tens of trillions of dollars a year in wages?
And there it is, the brutal economic gap. The fact that the lab's revenue is orders of magnitude off this figure. We're talking low billions, not trillions. That tells you everything. The models are nowhere near as capable as a generalized human worker.
If they were, they'd be priced that way, and they'd be diffusing way faster into the economy.
And this shortfall, it forces us to talk about the shifting definition of AGI. AI proponents are right to criticize the skeptics for repeatedly moving these goalposts.
That's a fair criticism. I mean, if you had shown Gemini 3 to researchers back in 2020, most of them would have been certain it could automate half of all knowledge work, like immediately.
So what's the rational response to that? We keep solving what we thought were the big bottlenecks reasoning, few-shot learning, but we're still not seeing that trillion-dollar economic impact.
The rational response is to realize that the original definition of AGI was incomplete. It's not to double down on the original timeline. It's to say, wow, there's a lot more to intelligence and labor than I previously realized.
It's not just about reasoning. It's about context, judgment, and how you acquire specialized skills on your own.
Precisely. And that leads to a prediction. The models will keep getting more impressive at the rate the short timeline people predict, passing new tests, writing better texts.
But they'll only get more economically useful at the rate the long timeline people predict.
And we expect the goalposts will just keep shifting. Even if the labs hit, say, hundreds of billions of dollars in revenue a year, by 2030, we'll probably realize we still need X, Y, and Z capabilities before we get to full automation.
Which brings us all the way back to the efficiency of the training methods. If the economic returns aren't there and the methods are so clunky, we have to ask, what exactly are these labs scaling?
That is the critical question. What are we actually scaling? And the sources draw a really sharp contrast between two types of scaling that often get dangerously mixed up in public discussions.
Okay, so the first one was pre-training scaling.
Yeah.
And that was beautiful, right? You just increased the model size and the data,
Hmm.
and it followed this clean power law trend. It was predictable.
Almost like a physical law of the universe. But the prestige of that predictable scaling is being used, I would say, laundered to justify these really bullish predictions about the current method, which is reinforcement learning from a verifiable reward.
What's the key difference? Why is RL scaling so much murkier?
We have no publicly known trend for it. With pre-training, more compute reliably gave you a certain boost. With RL, you're relying on human feedback, on these constructed reward environments, and that feedback is just inherently noisy and hard to generalize. We just don't know how well it scales.
Or if it just hits a wall of diminishing returns really fast.
Exactly. And when you look at the scarce public data points we do have, the implications are pretty bearish on efficiency. Toby Board's analysis connected some O-series benchmarks, and it suggested something pretty shocking.
What was it?
His analysis suggested that to get a capability boost similar to going up just one single major GPT level, we need something like 1,000,000x scale up in total RL compute.
Wait, 1,000,000x. A
Ugh.
million times the compute for just one incremental step up.
1,000,000 times.
That's not exponential progress.
Right.
That is catastrophic diminishing returns.
What?
It basically proves the current RL methods aren't the magic bullet for AGI.
It means you have to pivot. You have to find an algorithmic solution. If brute force scaling is this inefficient, the focus has to shift to the true driver of intelligence.
Which is continual learning, CL.
Exactly. Think about how humans get better over a career. It's not from one giant boot camp at the beginning. It's from constant experience, gained and incorporated in the relevant domain, day after day.
So solving continual learning, the ability to learn efficiently and contextually on the job, that's the real path forward.
That's the only way to overcome this clunky hard-coding methodology we're stuck in.
And Baron Miller suggested a pretty fascinating future architecture for this, built around a swarm of these CL agents.
Yes, the vision is that you have these individual continual learning agents out in the world doing different jobs, generating specialized value, and then periodically they bring all their specific contextual learnings back to a central hive mind model.
And that hive mind performs what's called batch distillation. So for those of us who aren't ML experts, what does that actually do?
You can think of the hive mind as the central brain, or maybe the senior partner at a huge consulting firm. The individual agents are the specialized consultants out in the field.
Okay.
They come back, and the master model aggregates all their specific, hard-won, contextual knowledge, the stuff that only works for client A or in lab B, and it generalizes it across the whole system. It's a central brain digesting field reports and improving the core engine for everyone.
That sounds like the necessary step to solve that contextual judgment problem we talked about.
Yeah.
But is this just going to appear out of nowhere and cause a singularity?
Highly unlikely. The best analogy is the progression of in-context learning, ICL. When GPT-3 launched, the paper was literally titled, "Language Models Are Few Shot Learners," and ICL felt revolutionary.
But it wasn't solved in 2020, not by a long shot. It took years of incremental progress. Things like chain of thought, better tool use, huge context windows to make ICL truly reliable for complex work.
And continual learning will follow that exact same path. Some lab will release an initial version, and it will be a major breakthrough. They'll call it CL. But true, robust, human-level, on-the-job learning that can handle all that nuance. That'll probably take another 5 to 10 years to really iron out.
And because it progresses incrementally, competition stays fierce.
It doesn't diminish. It stays fierce.
Which is the final piece that sort of neutralizes those fears of runaway games or a game set match singularity like Sam Altman sometimes talks about.
Right. If it all just appeared instantly, maybe. But if the initial breakthrough just leads to your competitors reverse engineering it and improving on it slightly, which is the historical norm,
Then the advantage is always short-lived.
and the competitive landscape confirms this, right? The big three model companies are constantly rotating around the podium. Every few months, someone else has the best model. It shows that all these supposed flywheels, synthetic data, user engagement, they haven't really done much to stop competition.
Talent poaching and reverse engineering just neutralize any advantage almost immediately. So what does this all mean for you, the listener? This deep dive reveals that the focus has to shift. It can't just be about scaling brute compute or continuing to hard-code skills. The real barrier to AGI is the fundamental algorithmic problem of achieving continual, context-aware semantic learning.
Until that is solved, the massive economic returns that AGI implies will stay just out of reach. Progress is undeniable, but the capabilities you need, that ability to acquire specialized, self-directed knowledge that adapts to context, that's just far more complex than the short timeline advocates often acknowledge.
So given the huge cost and inefficiency of just front-loading skills into these models, we want to leave you with a final provocative thought.
Think about your own day. What specific, highly contextual tasks that you perform do you believe are currently least susceptible to automation? And what kind of learning mechanism would an AI need to actually crack them and to do it efficiently?